Last time, we learned how to find the eigenvalues of a matrix, and for each eigenvalue, find the associated eigenspace, which contains the eigenvectors for that eigenvalue. We explored the geometric meaning of eigenvalues and eigenspaces. We also saw that when there is a basis of eigenvectors, then it becomes relatively straightforward to compute the action of a matrix or a matrix power on an arbitrary vector. That's because when there is a basis of eigenvectors, the arbitrary vector can be written in terms of eigenvectors, and the action of a matrix on an eigenvector is easy to compute. So in this lecture, we want to examine under what conditions we have a basis of eigenvectors, because this is such a nice situation to be in. First, we should talk about what it means to change basis. Remember that a basis for Rn is a set of vectors that is linearly independent and spans all of Rn. And remember, the key thing about a basis is, if you're given any vector in Rn, you can write it as a linear combination of basis vectors in exactly one way. So if there is only one way, then we call the coefficients of that linear combination the coordinates of the vector with respect to a basis. Coordinates are just a way to tell me how much of each basis vector to use to describe a given vector as a linear combination. For example, we usually use the standard basis to express a vector. In the plane, the standard basis vectors are e1 and e2. The vector e1 points right 1 unit, and e2 points up 1 unit. The standard basis produces a set of horizontal and vertical grid lines. And I can read the coordinates of a point from this grid. For instance, the star point on this diagram is at the point 1, minus 2 on this grid, which means I march to the right 1 unit and down 2 units. Another way to see what the grid is doing is it is telling me the coefficients of e1 and e2 that I need to produce a given point on the grid. So the star point is 1 times e1 minus 2 times e2. Now, the standard basis is not always the best basis to use. For instance, if I have a rocket ship with 2 thrusters that move in particular directions, W1 and W2, then it may be easier to express a vector in terms of W1 and W2. How can I find the linear combination of W1 and W2 that would produce a given point like 1 minus 2? Or in other words, how can I find the coordinates of 1 minus 2 with respect to a new basis, W1 and W2? I can view this question geometrically by drawing a new grid corresponding to W1 and W2. The grid will fill out the entire space if W1 and W2 span all of R2. And I can read off the coordinates of any point in the new grid if I want, and that will be the coefficients of W1 and W2 I'm looking for. For instance, look at the star point again. We saw in the standard basis its coordinates are 1 minus 2. In the grid from the new basis, I can get to the star point from the origin by first moving in the direction minus W1 by 1 unit, and then moving in the direction minus W2 by half a unit. This means the coordinates in the new basis are minus 1 minus a half. That's the geometric view. If I want to compute the coordinates in the new basis algebraically, then I should form a matrix P that contains the new basis as its columns. Then as a linear combination of new basis vectors, the star point can be expressed as P times the vector of new coordinates. On the other hand, if you form a matrix with the old basis as its columns, that's just the identity matrix. Then this star point, as a linear combination of old basis vectors, must be the identity matrix times 1, comma, minus 2, which is just 1, comma, minus 2. This shows that p times the new coordinates are just the standard coordinates. So what you see from this discussion is the following useful way to understand the action of p, the matrix with the new basis as its columns. Multiplication by p on the left takes a vector of coordinates in the new basis to standard coordinates. This means multiplication by p inverse takes a vector of standard coordinates to coordinates in the new basis. And if you're wondering why p inverse exists, it's because the invertible matrix theorem says an n by n matrix is invertible if its columns form a basis for Rn. So one way to view an invertible matrix like P is that it acts like a change of basis. So keep this in mind as we discuss when we can find a basis of eigenvectors. Let's do an example. Suppose we want to know how to express the vector -1, 18 in terms of the basis consisting of the vectors -2, 9, and 1, 0. Then we let P be a matrix with -2, 9, and 1, 0 as columns. Then P inverse can be computed to be the 2 by 2 matrix with entries 0, 1/9, 1, and 2/9. If you take P inverse and multiply by the vector -1, 18, you'll get the vector 2, 3. And these are the coefficients we were looking for, because you can check 2 times -2, 9 plus 3 times 1, 0 is indeed -1, 18. Now let's take a few minutes to explore the connection between the eigenvalues of a matrix and its determinant, since this will be useful for us as well. You may recall that our process for finding eigenvalues of a square matrix A began by subtracting a variable lambda times the identity matrix. This was equivalent to subtracting the variable lambda from each of the diagonal entries of A. We then took the determinant of this matrix. Because of the variable lambda, the expression for the determinant will be a polynomial in lambda. This polynomial has a special name. It's called the characteristic polynomial of the matrix A. You can see from the recursive determinant formula that one of the terms will involve multiplying the quantity minus lambda n times. So the characteristic polynomial will have degree n, meaning n is the highest power of lambda that appears. Now, the fundamental theorem of algebra, which you may have learned in school when you first learned about polynomials, says that an nth degree polynomial always has n roots. Some of these roots may be complex or repeated, but if you count them all, you will get n of them. You may also recall that these roots appear in the factorization of the polynomial. If lambda is the polynomial variable, and lambda 1 through lambda n are the roots, then the polynomial factors as a product whose terms are quantity lambda minus lambda I, with a -1 to the n in front to account for the sign of the largest power of lambda. We can find the eigenvalues of A by setting the characteristic polynomial of A equal to 0, and this is called the characteristic equation. This means the eigenvalues are just the roots of the characteristic polynomial. So the lambda I in the factorization must be the eigenvalues of A. On the other hand, if you look at the factored expression for the characteristic polynomial and set the variable lambda equal to 0, you get the determinant A on the left side and the product of the eigenvalues on the right side once you clear all the negative signs. So the determinant of a matrix is the product of its eigenvalues. This is an important fact that also makes intuitive sense if you recall that the eigenvalues are the expansion factors under multiplication by A in certain special directions. But the determinant is a kind of overall expansion factor. It's how much the volume expands under multiplication by A. So let's see whether this is true in an example we explored last time. For the 2 by 2 matrix A, with entries 1, 2, 5, 4, we saw it has eigenvalues -1 and 6. So the product of the eigenvalues is -6. You can check that the determinant of this matrix is 1 times 4 minus 5 times 2, which is also minus 6. So we see the determinant is the product of eigenvalues in this example. From this fact about the product of eigenvalues being the determinant, we see a new criterion for invertibility. Since a number is 0 if and only if at least one of its factors is 0, and a matrix having 0 determinant is equivalent to the matrix being not invertible, this means that a matrix has a 0 eigenvalue if and only if it is not invertible. You can add this as yet another criterion to the invertible matrix theorem, which tells us when a matrix is invertible. Okay, now let's try to understand when we have a basis of eigenvectors. Since we want a basis of Rn, we're only going to be interested in eigenvalues that are real numbers and eigenvectors that have real entries. The eigenvectors of a matrix, as we've seen, play a special role as special vectors that geometrically describe directions that do not change under the transformation represented by that matrix. And we've also seen that when computing matrix powers, it's helpful to have a full basis of eigenvectors. But when is that possible? It turns out that the answer is related to the number of repeated eigenvalues a matrix has. So let's give this a name. Remember that the determinant of A minus lambda I is a polynomial in lambda called the characteristic polynomial of A. And we find the eigenvalues of A by taking roots of the characteristic polynomial of A. So let's define the algebraic multiplicity of an eigenvalue to be the number of times it appears as a root of the characteristic polynomial. So if an eigenvalue appears twice, then its algebraic multiplicity is 2. Note that the sum of the algebraic multiplicities has to be less than or equal to n, since the number of real eigenvalues, counting multiplicities, is at most n. But it could be fewer if there are complex eigenvalues. Let's investigate some examples to see if we can figure out what the algebraic multiplicity has to do with having a basis of eigenvectors. Look again at the 2 by 2 matrix A with entries 1, 2, 5, 4, which we've studied before. We saw that its characteristic polynomial can be factored as lambda plus 1 times lambda minus 6. So its roots, minus 1 and 6, both have algebraic multiplicity 1 because they appear once each as roots of the characteristic polynomial. We already saw the eigenvalues had associated eigenvectors 1, minus 1 and 2, 5 that formed a basis of R2. Consider another example. Let A be the 2 by 2 matrix 9, 2, 0, 0. Its eigenvalues are roots of the determinant of A minus lambda I, which is the determinant of the matrix A with lambdas subtracted off the diagonal. This is just 9 minus lambda times minus lambda. To find the roots, you set that equal to 0, and you get the eigenvalues 0 and 9. Since they're not repeated, each of these has algebraic multiplicity 1. We can compute the eigenspaces now as the null spaces of A minus 0i and A minus 9i. And as practice, you should check, with some work, that the eigenspace E0, which is the null space of A minus 0i, is just the span of the vector minus 2, 9. And the eigenspace E9, which is the null space of A minus 9i, is the span of the vector 1, 0. And the two eigenvectors, minus 2, 9 and 1, 0, do form a basis for R2. Geometrically, what happens along the E9 eigenspace is that the vectors along E9 get expanded by a factor of 9. And along the E0 eigenspace, they get multiplied by 0. So all the vectors in that eigenspace immediately get contracted to the origin. Any point that's not on these eigenspaces will contract in the E0 direction and get multiplied by 9 in the E9 direction. So this star goes to this dot because its components get multiplied by 0 in the E0 eigenspace and get multiplied by 9 in the E9 eigenspace. We can also see from this diagram why having a 0 eigenvalue means the matrix A cannot be invertible. That's because the contraction along the E0 eigenspace sends all those points to the origin. So there's no way to invert this transformation. Both the examples we've seen so far had no repeated eigenvalues, and it also had a basis of eigenvectors. Let's look at an example with repeated eigenvalues. Let A be the 3 by 3 matrix with these entries: 3, 8, 0 in the first row, 0, 3, 0 in the second row, and 0, 0, 7 in the third row. Subtracting lambdas off the diagonal, and then taking its determinant, we see that this matrix is upper triangular, and so the determinant is just the product of the diagonal entries. We obtain the characteristic polynomial 3 minus lambda squared times 7 minus lambda. That's a cubic with roots 3, 3, and 7. So the eigenvalues in this case are 3 with algebraic multiplicity 2, since it's repeated twice, and 7 with algebraic multiplicity 1, since it's not repeated. As an aside, you might have noticed that 3, 3, and 7 were the eigenvalues, but they were also the diagonals of A. That's no coincidence. Because the matrix A was upper triangular, the determinant of A minus lambda I was easy to calculate, and the characteristic polynomial has as its roots just the diagonal entries. In other words, for upper triangular matrices, the eigenvalues are just the diagonal entries. Okay, so we have a situation where we have a repeated eigenvalue. Let's see what happens with the associated eigenspaces. I claim the repeated eigenvalue may have an effect on the dimension of the eigenspace. And I want to use this example where the eigenvalues are easy to see because the matrix is upper triangular, to give you at least a sense of why this might be true. To find E3, the eigenspace associated with the eigenvalue 3, we want to find the null space of A minus 3i. The effect of subtracting 3 times the identity from A is that it produces 2 zeros along the diagonal of A, and the resulting matrix is already close to row echelon form. So you just have to switch the last 2 rows. Now recall that the dimension of the null space of A minus 3i, called the nullity of A minus 3i, it is the number of columns of the row echelon form of A minus 3i that do not have a leading entry. In this case, you see that there is only one column with no leading entry, so the nullity is 1. However, notice that if the 8 in this matrix had been a 0, there would be 2 columns with no leading entry, and the nullity would be 2. And I claim that for any other upper triangular matrix A with eigenvalues 3, 3, 7, the nullity of A minus 3i is only ever going to be 1 or 2. You know it's at least 1 because A minus 3i must have determinant 0. But it's never going to be more than 2, essentially because the matrix A had only 2 diagonals that were 3, and so A minus 3i was only going to have at most 2 columns with no leading entries in them. Now, this is not a proof, just a plausibility argument for a matrix that was upper triangular. But essentially, you can generalize these arguments to any matrix, upper triangular or not, to see that the dimension of the eigenspace associated to an eigenvalue is always going to be less than or equal to the number of times the eigenvalue is repeated. So let's define the geometric multiplicity of an eigenvalue, lambda, to be the dimension of E lambda, the eigenspace corresponding to lambda. Then the following fact is true. The geometric multiplicity of lambda is always less than or equal to the algebraic multiplicity of lambda. This insight can help us see some things. For instance, suppose all the eigenvalues are real. Then if the geometric multiplicity of lambda equals the algebraic multiplicity for every eigenvalue, then since the sum of the algebraic multiplicities is n, the sum of the geometric multiplicities also has to be n. In that case, you'll have a full basis of eigenvectors. Namely, just take a basis for each eigenspace, because as we'll soon see, eigenvectors from different eigenspaces must be linearly independent. But if the geometric multiplicity is strictly less than the algebraic multiplicity for some eigenvalue, then we're in the undesirable situation where there won't be a full basis of eigenvectors, because there won't be enough dimensions in the eigenspaces to span all of Rn. For example, if you have a matrix with eigenvalues 3, 5, and 5, the dimension of E5 must be either 1 or 2. If the dimension of E5 is 2, then there is a basis of eigenvalues, because you could just take the union of a basis for E3, which has one eigenvector direction, with a basis for E5, which has two eigenvector directions. This is because we'll show in a minute that eigenvectors from different eigenspaces are linearly independent. So you'd have 3 linearly independent vectors in R3, which must span R3. But if the dimension of E5 were 1, then since the dimension of E3 is 1, we could only have 2 linearly independent eigenvectors, and that would not be enough to span R3. So in that case, there is no basis of eigenvectors. All right, let's see now why eigenvectors from different eigenspaces must be linearly independent. The theorem says this: if V1 through Vk are eigenvectors of some matrix corresponding to distinct eigenvalues lambda 1 through lambda k, then the eigenvectors are linearly independent. There's an easy way to make this plausible. If there were a set of eigenvectors that were not linearly independent, all from different eigenspaces, then one eigenvector, call it W, would be a linear combination of the other eigenvectors. But because W is a linear combination of other vectors from different eigenspaces, multiplication by A would stretch each component of W from different eigenspaces by different factors. So the vector AW will have to get skewed in a different direction than W. It cannot be a multiple of W, as was to be shown. Now we're ready to characterize when an n by n matrix has a basis of eigenvectors that span all of Rn. If we have a full basis of eigenvectors, call them V1 through Vn, then let P be the matrix with those eigenvectors as its columns. Let D be a diagonal matrix with eigenvalues down the diagonal and 0 everywhere else. The eigenvalues should appear on the diagonal in the same order as their corresponding eigenvectors appear in the columns of P. Then, if you assemble these matrices like that, I claim AP equals PD. The reason is that this is really just expressing the eigenvector equation, AV equals lambda V, for each lambda simultaneously. Then AP is just A times a matrix with VI as columns. If you think about how matrix multiplication operates, that's just the matrix with A times each VI in the ith column. But then the eigenvector property shows that the ith column is lambda I times VI. But that can be verified to just be the matrix P times the diagonal matrix D. So indeed, AP does equal PD. Now, if you multiply both sides on the left by P inverse, you get P inverse times A times P equals D. So having a full basis of eigenvectors means that you have this property. P inverse AP equals D. Conversely, if you have this, then AP equals PD, which means that the eigenvector equation holds for each column of A. So the columns of P then form a full basis of eigenvectors because P is invertible and the entries of D are the associated eigenvalues. So let's give this property a name. We'll call a matrix A diagonalizable if there exists an invertible matrix P such that P inverse AP equals D, a diagonal matrix. If so, then the columns of P are the eigenvectors of A, and the diagonal matrix D contains the eigenvalues. So using our earlier example, with A, the 2 by 2 matrix 1, 2, 5, 4, we see that if we form a matrix P with columns that have the eigenvectors, 1, minus 1 coming from the eigenvalue minus 1, and 2, 5 coming from the eigenvalue 6, then you can easily check that if you compute P inverse times A times P, you will get the diagonal matrix with diagonal elements minus 1 and 6. Notice the minus 1 comes first because the associated eigenvector 1 minus 1 was the first column. We proved all the ingredients in this theorem, which says that being diagonalizable is equivalent to having a basis of eigenvectors. And that's equivalent to having the geometric and algebraic multiplicities being equal and all eigenvalues being real. One special case of this is that if you have a matrix with n distinct real eigenvalues, in other words, there are no repeated eigenvalues, then the matrix A is diagonalizable. This follows by noting that the algebraic multiplicity is then less than or equal to 1. But this is always bigger than the geometric multiplicity, which is always at least 1 because there's an eigenvector. So both geometric and algebraic multiplicities must be equal to 1, and so equal to each other. So the theorem shows that A is diagonalizable. There's another useful way to view diagonalizability. It means that there's a change of basis that turns the action of a given matrix A into one that behaves just like a diagonal matrix with respect to a new basis. All the diagonal matrix does is scale the axes directions by various factors. So if we express A as PDP inverse, then look at what happens. If you're expressing vectors with coordinates in the standard basis, then the claim is that the action of A will look just like the action of first multiplying by P inverse on the left, which changes coordinates in the standard basis to coordinates in the new basis, then performing D, which scales the axes in the new basis, then changing the new basis back to the standard basis with P. And so that's why A equals P, D, P inverse. We have a special name for matrices that are related by a relation like the one in the definition of diagonalizability. We'll call two square matrices A and B similar if there is an invertible matrix P such that B equals P inverse times A times P. If you think of the invertible matrices P and P inverse as changes of bases, then one way to think of similar matrices is as they represent transformations that are doing exactly the same thing, just represented in different bases. So then you should expect that similar matrices would share some similar characteristics. For instance, similar matrices have the same determinant. You should try to show this. Also, can you similarly show that similar matrices have the same characteristic polynomial? Try this. Therefore, they have the same eigenvalues. However, similar matrices do not have the same eigenvectors. They have the same rank and the same state of invertibility, meaning one is invertible if and only if the other one is. We've seen many examples now where the matrix powers are important to compute, and diagonalizable matrices have matrix powers that are very efficient to compute. First, notice that matrix powers of similar matrices are related in a cool way. If B equals P inverse AP, remember that means A and B are similar, then when you take the kth matrix power of B, it's very easy to see how it's related to the kth power of A. If you take B and multiply it many times like this, then the P and the P inverses pair up and cancel. So B to the K is just P inverse times A to the K times P. For matrix A to be diagonalizable means A is similar to a diagonal matrix D. P in this case is just the matrix whose columns are eigenvectors of A, and D consists of eigenvalues along the diagonal. Then the prior discussion shows that P inverse times A to the K times P is D to the K. That D to the K is very easy to compute because you just raise the diagonal elements to the kth power. You might pause the video and try some examples to see why. Then rewrite the expression like this, as A to the K equals P D to the K P inverse. Let's look at our example. If I want to find the kth power of the matrix A with entries 1, 2, 5, 4, I can do this more easily as P, the matrix with eigenvector columns, times the diagonal matrix to the kth power times P inverse, whatever that is. This is very fast because it doesn't require as many operations to complete as a normal 2x2 matrix power. And next time, we'll use these insights to return to our applications, populations of foxes and rabbits, in the next lecture, to see what we can learn from that model.